And I guess I want to talk a bit on how to approach designing for a project like this, where we have three components, more or less, that are kind of independent. So we have our cube that then talks to AWS IoT, and then, or more like black boxy. So it talks to AWS IoT, and then there is a browser thingy that talks to whatever here is, and how we can, when we want to build something like this, and we have kind of three teams. So we have a firmware team here, and then we have a backend team here, and then we have a front-end team here. How can we make sure that they align well? Because in the end, what's really important is that we're not building three products. There's not a front-end product and a back-end product and a firmware product, but there is just one thing that we build for the user. So from the user's point of view, it doesn't matter, like that you have three teams, that you made this decision that you're gonna have three teams. And the decision is probably smart. It's kind of normal to divide a task like this into three teams because you are 7 people. So you have resources that are way too many to just focus on one thing. Like having 7 people work on firmware, figure that out, and then move over to the backend doesn't make sense. We never have this case. We very often have the case where we have different skills. We have people who have backend experience, because this is an entire domain where you can spend kind of a lifetime learning on just the firmware and the hardware part. And then the whole cloud part is completely different in terms of what skills you need. So this is an entire career. And then front-end engineers, that is an entire career. Like you can fill your entire lifetime working on front-end applications because it is extremely complex. All of these three domains are so distinct and so complex that it makes sense that we separate the workload. Now, and it's important to realize that all these domains have different needs and different requirements and also different capabilities. And when we in this setup, kind of the least common or the most important part that we have to focus on is actually the hardware, because the hardware has the biggest constraints in terms of what the bandwidth is that we have here when it comes to sending data, what the energy we can consume is, the compute power that we have, because here, like, none of this matters. We have in practice unlimited bandwidth, we have unlimited energy and unlimited compute. We can scale up as much as we want. Front end has some of these limitations. We can't just like force the user to download gigabytes of data for a web application. So there are some limitations here, but they are many, many magnitudes, probably 1,000, 10,000 times bigger than what we can do on the firmware. Even when it comes to compute, we have a PC here that can run our UI. So what really will in the end drive a bit all these decisions when it comes to how do these things communicate together, they will be driven by our firmware component, and then specifically the NRF9160 that's in there, because that it doesn't have a gigabyte like uplink. We can just stream real-time data from the sensor that is on there. So there is the accelerometer that we're going to use to detect which side is up. That accelerometer that can give you real-time milliseconds updates on the positioning. We have shown on the Thingy 52, there's a mobile app where you basically get a real-time visualization of the cube, how you move it. And that is possible because BLE connection has more or less a few milliseconds latency, and the bandwidth is multiple megabytes if it's really short next to each other. So that's enough to send over real-time motion data. But that won't work via LTE. So that's something you cannot do. So that will be one of the first constraints that we have to think about when we consider what kind of data is the user interested in. And we've established in this project, we want to build a habit tracker that is based on which side is up. So I gave you kind of these ideas and said, okay, we're gonna want to be able to track like which side did I now put up and when. Because we want to do stuff like counting. I want to count every time I have a coffee. I want to kind of put the coffee side up so I know how many coffees I consumed during the day. That's one concrete example that I can imagine. And then I want a kind of time tracker. Let's say I do exercises every day and then I put it on the exercise side and then now the timer starts. And when I'm finished, I turn it onto the finished side and then the timer stops. So what I'm right now doing is from the user perspective, thinking, okay, what I'm interested in. And that should be the view that all of you three teams take all the time. Like it's really important that you take the user perspective. There is a technique for like keeping an eye on the user focus, but still being able to design a software system that's called domain-driven design. I don't know if you have heard about it, but it in the end establishes a ubiquitous language. That means a language that like all three systems use, so that when you in the teams start communicating with each other and say, well, I'm going to send you this face up event, and then the backend says, okay, it's not face up, but it's just like direction and number, and you say to the front end, hey, I'm going to send you a number, then you create these translations, which will be really problematic to create when you try to create a cohesive experience for the user, that like everybody talks in things in different terms. You need to establish a common language and basically develop states and events that describe how your system behaves from the user perspective, and keep that into, like this needs to trigger down into your software, because then you can also switch around between teams, and this is hopefully what will happen, that you start collaborating together on the different aspects. And then if in the front end you see a thing, the face up, you know this face up is coming from a face up event in the firmware. And the backend stores face up events in a database and doesn't store entries or I don't know, user actions. Yeah, so that it kind of becomes clear. Face up event is a face up event everywhere. So when we start thinking about the system, there's a DDD design technique called event storming, where you as a team can start describing how the system behaves through like the basic building blocks are very simple. Let's find a thing that works. There are events and there are commands. So you can describe your entire system with these two building blocks. And what we do in event storming sessions, these are sticky notes. One sticky note, the events is green and the commands is orange. And events are created based on commands. And so you can model the flow of events, like what happens when the user turns the face up of a cube. Then a face up event is created with a number. That event needs to be transmitted to the backend. The backend needs to, for instance, store this. So from this knowledge, because you know that this face up events maybe needs to arrive at the front end as well, you can then model the flow of information through your system using events. Not every system is actually an event-sourced system, but you will have communication between these systems, which will be event-based. That can mean you have real-time push notifications, or the front end can also poll for the latest events. But this technique is really helpful to get, again, an overview of what should the system do. In the first step, we don't focus on there is a backend and there is a front end and I have a website that needs a REST API. This is really implementation detail, and that can change over time. Like today you think, oh, I want a REST API, but in the future you think, WebSockets would be nice. And then you suddenly change from a pull API to kind of a pub/sub API, and then your entire infrastructure changes. However, if you have these artifacts here, you know what events are getting sent, what can a user do in a system, then that stays the same, regardless of how you change your implementation. So that's this would be the first step. Really think about, okay, what is it that I want the user to achieve? I've gave you two examples, like user wants, this is a bit kind of we develop these personas, yeah, so this is the coffee person, yeah, and then we have the exercise person, yeah. These are my two personas. They are customers or users of the system. So this one wants to count how many coffees per day they consume, and then this one wants to measure how much exercise they do per week, and maybe you have a goal. Like, it's not only how much they measure, they actually say, well, I want a reminder, yeah, I want a reminder if the time is too low, if I'm not exercising enough this week. Yeah? So that is now your user story for the system. And based on kind of that, what you want to achieve. And that's something any stakeholder can understand. Like, you can talk to your product owner, you can talk to your investor and say, this is what we're gonna do. Yeah? They don't care about, like, okay, there's an HTML website that talks with REST to an AWS IoT backend. That doesn't matter. Like, this is not the value that you're creating. The value is these use cases that you're implementing. And then based on your scenarios, you can start, okay, if I want this, yeah, what kind of information do I need to solve this use case? So what are some of the events I can get from the cube? What can it do? Like, we've decided that it has 12 sides. It can detect which side is up. It can be turned on and off. That's kind of limited. So if I want to achieve this here, the coffee counter, what do I need to do? What kind of events are there? that will allow me to show the user a coffee counter, like face the coffee side up. Every time they move the coffee side up, we increase the counter. So now, this is then where the interesting part starts. It's like, that sounds very easy to do, because the backend can just say to the firmware, hey, send me this event, yeah? And then I just increase a counter for this user, and then I'm done. The interesting part will then be in the firmware. It's like, how can we make sure that we really send, like, how do we detect this? And this will take some time. So the backend is like, I can go on vacation now or what? Like, so I just will wait for you until you figure this out. Yeah? And the firmware people are like, okay, this will take us 2 months. Yeah, to whatever. Like, we need some machine learning, we need to understand the system, we need to whatever, we need to do some testing. So, and this is where we can, if we are the backend team, we can already start together also with the firmware team discussing like, what should be the API that the firmware uses to notify us about this event. It doesn't matter when you get it, eventually we will get this information, coffee side up. So how do you gonna notify us about this? And that is the first decision that you kind of have to make, is to select a suitable protocol between firmware and the backend. So you want to send side up event, and then it has a number, let's say number 8, plus a timestamp probably. So you kind of have 3 values or 3 data points that you need to encode. You have a timestamp, you have the name of an event, or the string that this is a side up event. It can be a number if you want, this is our first event, and then you have some additional information in which side was it. Is it side 8, 12, or whatever? Now this is kind of that needs to be encoded, and you have an extremely wide choice. You can send plain text, you can create a REST API here, you can encode it in JSON, you can use protobuf. That depends a lot on again, a bit on the firmware side. Like, what can it do? How does the encoding work? And like, we know, for instance, that the JSON encoding, writing JSON is pretty painful in C, because JSON is a encoding format that has variable length everywhere. Everything is a number or a string, and the strings are kind of go forever. There's no structure, and that makes it especially painful to cram that into a statically compiled language, where you need to know exactly for every field that I have in my JSON object, I need to allocate memory, I need to know how long it is. And that is really pretty painful. So one good candidate could be protobuf or CBOR, because they kind of address that a bit. And they give you, when you have a schema for your messages, they give you kind of the encoders and create the code you can use to encode the payload that you want without having to manually write your own encoders. So now maybe you have you have come to this decision, and you also decided you're gonna use MQTT, by the way. So AWS IoT is amazing, but it only supports MQTT. And MQTT limits what network you can use, because MQTT requires TCP. You can't use UDP for that, which you can say, well, this is a consumer device, we're not gonna work everywhere in super remote locations. We can rely on having LTE available, and we want this interactivity. We want to more or less have a real-time experience. That means when the user turns this here, then one of the requirements is that this doesn't take like 5 minutes for the event to show up. Yeah? I want this is an important user story. Yeah? I want this more or less in, let's say a second. I always like, when I think about this, I'm like, okay, what is an acceptable time? I work in magnitudes. It's like, is 10 seconds okay? Probably not. Is 1 second okay? Yes, that's fine. Is 0.1 second okay? That would be awesome, but is it necessary? Probably not, and it's too hard to do. So I settle on roughly 1 second. So it should absolutely be less than 10, but ideally closer to 1. And then something in between is usually fine for the user. So back to, okay, now you made a decision on, let's use protobuf, and we use MQTT because that's not a decision. The decision has been made when you picked AWS IoT. That is a limitation. Of course, you could add we could add a CoAP adapter here. I have a demo project somewhere where we add a Leshan, which has an AWM to M implementation, which is CoAP in front of AWS IoT. But that then no longer is serverless. So this is a stateful instance of a service that you put in front of AWS IoT, and then suddenly your job becomes making this thing scalable. And that's not what we want. Like, that will cost money. We need people to host this thing. We need people to maintain it. We need to infrastructure to kind of reboot it and replace it, do security updates. That will cost to really have the same SLA what AWS IoT gives us, 99 and 5 nines probably, or 4 at least. We need to hire 3 people to guarantee this. So, and for kind of a prototype and an early stage project, this is way too expensive. So yeah, that is out of the question. So here's a bit how some of your decisions are made for you. Yeah? We can't afford that right now, so we have to go with AWS IoT because that will allow us to go on vacation, if it runs, and it will run, and we don't have to think about the infrastructure. So now still, that is what you can discuss with the firmware people because they can also do some testing here. Yeah? While some of the firmware people work on the big problem, how to detect the site and how to figure this out, they can do some smaller iterations where they're like, okay, let's try to get it to connect to AWS IoT, see how that works. How do I send a message there? How complex is it to send a JSON message, send a protobuf message, send CBOR? What do we prefer? And then the firmware team is like, okay, for us, we prefer protobuf because it's super, super small. Like the payload is the smallest that you can get. It's just pure binary, no metadata. That's awesome. And then the cloud has really no argument to not do it, because on the cloud we can run circles around any data format. So there's no argument. It's like, but it's kind of complicated. Yes, it is, but the benefits are really there. So, this is kind of a golden rule. It's like, if anything can be done in the cloud, do it in the cloud. And this is like, if I can enrich a datagram with metadata that I need for a human to understand, and I can do it in the cloud, let's do it here. Because here, any byte that we do not send saves us energy, saves us data costs, and reduces the risk that we need to resend the message. Because the bigger the message is, the higher it is that connection drops and that we run into an issue, and that it multiplies really every byte. So, and this is where then now the backend team can say, okay, we've agreed on, we're gonna get protobuf via MQTT, here's our message format, this is our protocol. And now you build your solution, you start talking, the front-end team in the meantime working on, okay, I know I need to build a UI for a user to count coffees. You can start discussing how this solution should look like, and what the UI features will be, and then you can talk to the backend people saying like, this is what I need from you. I need this kind of information. I need, for instance, a count. I need an alert. I need a summary. Or I want real-time data. I can do the summary in my app. That's fine for me. You can just give me the kind of the raw stream of events. That's something you can discuss. What payload do you want? What format is the same? Like, do we use REST? Do we use WebSockets? Do we encode in JSON? Do we use protography as well? That's another discussion. And now, since like these two things are typically like 10 times faster to change and to adapt than something in firmware, because this takes extremely long to implementation is a mess in C. Sorry, I'm not a big C fan, so I would call it a mess. But like I write in languages that are running in real-time interpreters. Like the C people will say this is a mess. I waste a lot of memory for that convenience. But I think nobody will argue that implementation takes much longer in a statically compiled language like C. So it takes a long time to get to a point, and then if you want to change something, it takes a long time again, and we can do this very quickly here. Especially since we have a system, that's the other beauty, that we completely control. Like when we roll out a project like this, then this is a web URL that the user types in, and these two things we own, and we can change at any point in time. We can push an update here now, and it's like committed, and it will be up in 10 minutes. Where in a firmware, that takes a while. Like the device needs to be online, we need to kind of be certain that the change is really necessary before we do a FOTA. A FOTA also blocks the device from usage. So kind of there's a big hurdle in changing software there as well. But the main point is that while the firmware team figures a lot of things out, and this will take a lot of time, because also debugging capabilities are much worse than compared to software, the pure software things. Here, when we run things in hardware, it becomes really hard to kind of know what's going wrong. You need to do traces. So all of this takes so much time that we need, in order to develop, start developing here in parallel, we will build and use a simulator. That's always a good thing to have. And the simulator, in the end, is a script. It can be a Node.js script, a Python script, whatever, that behaves like the firmware device. So it will use the same kind of connection and the same protocol. You just implement it in software. Meaning in Node.js, you use MQTT JS as the library that connects to AWS IoT using the same authentication device credentials. And then you implement like sending, for example, random sites on a timer, or you can make it a CLI and say, let's send site 1, and then you connect, send site 1, disconnect, and then you get an event into here. And this is different than writing end-to-end tests. I will talk about this soon, but this is something that the backend people can use, because you can then use this to like see how these events flow through your system and correctly get persisted and whatever while developing it. But also you can give this to the front-end people. Like the front-end people, if you want to be sure that kind of the flow of events works correctly through the backend, then you can use the simulator to send data through the backend. However, I also recommend for the front-end people to use like more or less a simulator here that purely works with your front-end. because your front end has a connection to the backend that could be REST, and instead of like pulling data from a REST API that's powered by the backend, you can do the same thing and have a local web server that serves you JSON files, or you can have you can inject data in your app purely in JavaScript. So if you have a React app, then you have somewhere you have a context that stores the latest events, and you can manipulate this with a component that is able to simulate data as if it came from a REST API. If you build your front end like this, then you have kind of a built-in way to like change and develop your front end independently from a running backend. You don't need the production backend, you don't need the development backend, you don't need to care about how to get this. Because in the end, the contract that you have is not, I need a database for the thing to work. The contract that you have to the backend from the front end is, I have my API here, let's say it's REST, that I can call, and here are the JSON objects that I get back. This is the thing that you depend on. And it is not like, this is kind of it doesn't matter for the front end application where this data is coming from. So that is where these simulators are very good, because in the end this also helps to clarify your assumptions about the API. If you write a simulator, then you also understand and can kind of show the firmware people, here's our simulator, this is the data that we are expecting, this is the shape of the data that we've agreed on, and they can look at it and like, no. That's like this field, we don't set this, or it's a different field, or whatever. This process of clarifying your assumptions and your contracts between these systems is super important. And the important part is you really need to put this in code. Like, it doesn't help if you put it in a Confluence page or in a wiki page and say this is the fields that we have. No, it needs to be in code somewhere, and this is then where we need to talk a bit about an end-to-end testing. This becomes really important when to make sure that your implementation actually works with the protocol that you have defined. Is like, you want to set up tests that treat your entire system kind of as a black box. And really, you have your backend here, you put in your events from the firmware, and you get front-end events out. And your end-to-end test is an automated test that you can run every time you change your system that simulates this entire chain. It doesn't look at like, and for the end-to-end test, it doesn't matter that, oh, this event maybe needs to be stored in a database. It's completely irrelevant. What matters is that the end-to-end test really describes, given the device sends me this side up, what is the front end receiving? And there may be some conditions, like the user has said that side up is my coffee side, and so given the user has done this configuration, like what will the user receive when then the device sends in the side? And what you get out of that is then really like a high-level bird's eye view of the entire system, and that every party here can reason with. And this is especially, and that like kind of, for the firmware side, it doesn't make so much sense, but it makes a lot of sense for the backend, and it also makes sense for the front end. The front end can do the same and say, given I get this event from the backend that says firmware side is up, then I can display in this component whatever. So what the beauty there is that you really incorporate the messages or that you passing between the systems into your automated tests, and that they are documented and they show that they are working. Because like very often I see that backends are tested, are unit tested, and maybe integration tested. Unit testing meaning like you maybe have a message converter that takes a protobuf input and converts it to a JSON object so that you can store it. You have a unit test for that, so that's awesome. But you don't actually show when is this getting used, and it might not even be used. You just have a unit that says, okay, I can convert protobuf to JSON, but then what? And then you have an integration test, maybe. You take up, you take your database and you show, okay, I can persist events. But your like persistence integration test will be super generic. It will not be, I can store side up events, because from a like implementation point of view, it doesn't matter. Like all the events will have the same shape, they have the same properties, they have a name, they have a timestamp, and then they have some payload. So you will write an implementation that can store arbitrary events, because that's efficient. So your integration test doesn't even share that. Maybe it says there's a side up event, but maybe there's another event. There's a power on off event, there's a load charge event. For the integration test, that doesn't matter because they are all the same. So once you've shown you can store one event, you can show any event that like fits this interface of your events. And since you control the backend, all the events will have the same interface. That also doesn't tell you a story what the system can do. From these two tests, I know, okay, it does something with protobuf and it can store events. But we need a way to show how does this user story really connect to what does the backend fulfill this user story. This is pretty important to show that we can really write a test that reflects this one user story. I wanted to see a test that says, okay, the user configures a coffee counter limit, and then his device sends in 4 coffee counters, then the limit is not reached, and it sends in the 5th, and then I get a warning. And this is really the use case that we have here. And if we have this, then we can really reason well about the entire system if the solution that we're building is implementing what we actually want to do here.